Hey guys, so today we'll be talking about the Hubble's Law and the Big Bang Theory, and then we'll be wrapping up this chapter. And in the next video, we'll be doing some past paper questions. So, this is Mr. Edwin Hubble, who came up with the Hubble's Law. Pretty decent looking guy, eh? So, let's start off with, and also very classy. Let's start off with Hubble's Law. Okay, so first, let's talk about what the Hubble's law basically says. So, what happened was that Mr. Hubble found that the spectra from faraway galaxies appeared to be redshifted. So, I'll show you what that exactly means. So, for example, this is situation 1. This is situation 1, and this is the Earth. This is the Earth. I'll write E for Earth, and this is a star, and this is a star, right? And the light coming from the star has a wavelength like this, because the light is a wave, so it comes in wavelengths, right? So this is the wavelength of the star, right? So we can call this the initial wavelength, right? And after, now we look at situation number 2. This is after a few years, right? So this is what Mr. Hubble observed, that after a few years what happened was that the Earth is here, and the star, the distance between the star and the Earth increased. So what happened, and how did Mr. Hubble know this? He knew because the wavelength that was observed on the Earth became longer. So what happened was that the star appeared to be red, and this is what we call the redshift. So we can say that the star now appeared redshifted. Now you can see that the wavelength increased significantly. So now you can see the wavelength increased. Now you might ask, why do we call it redshift only if the wavelength is increasing? And the answer to that is that if we look at the light spectrum, the highest or longest wavelength is for the red light, right? So if you increase the wavelength of a light wave, the color will automatically go red, right? So the shortest wavelength is violet or purple, and the longest wavelength belongs to the color red, right? So if you increase the wavelength, the color will be red, right? So this is why we call this the redshift, and this is how Mr. Hubble found out that the Earth and the star had moved away after a few years. So what this implies that the universe is expanding, right? This is a very important concept, and this is deeply linked with the Big Bang theory as well. So Mr. Hubble then came up with an equation which we call the Hubble's law, and the equation, let me scroll down. So the equation goes like V is equals to HO into D, right? Now V is the recessional speed. Now you might ask, what's a recessional speed? So let me just get back to that. Recessional speed. HO is the Hubble's constant. This will be given in the paper. Hubble's constant. And D is the distance from wherever you're measuring. So in this case, it will be the Earth, distance to the Earth. to the Earth. Now this equation implies or tells us that v is directly proportional to the distance. Now this means that if the distant star will move away from the Earth faster compared to a star that is closer to the Earth, right? So let me draw this out. So if this is the Earth, E, and this is star 1, and this is star 2, this is star 2, and this is star 1. Star 2 will have a greater recessional speed, and recessional speed means the speed with which the star moves away from the Earth, right? So the recessional speed for star 2 will be greater than the recessional speed for star 1. So we can say that V2 is greater than V1. So this is what is implied by the Hubble's law. V is equals to HO into D, and this way you can also find the distance to the Earth, right? If you know the recessional speed and you use the Hubble's constant to find the distance to the Earth or from wherever you're measuring, right? So there's a graph as well which helps you understand this concept better. So the graph, the graph goes like we have v, the recessional speed on the x-axis, and d, the distance to the Earth on the y-axis, right? V can be taken in meters per second and d in meters, right? So the graph is like this, and this shows us that at higher distances the recessional speed is higher, and at lower distances, shorter distances, the recessional speed is lower. So this clearly implies and shows what the Hubble's law means, right? So that's the Hubble's law, and that's all you need to know for our syllabus. Now we move on to the Big Bang theory, and this will require a physical demonstration. So I'll move on to video, and I'll show you exactly what the Big Bang theory implies and what it talks about. So see you. Okay, so this is what the Big Bang theory or the Big Bang model talks about. The Big Bang model says that the Hubble's law implies that galaxies are moving away from each other, right? For example, I'll draw a galaxy on my forefinger and a galaxy on my thumb, right? So this is galaxy 1 and this is galaxy 2, right? Now what's happening? The Hubble's law is saying that the space is expanding and the galaxies are moving away from each other, right? So initially the galaxies were close, and with time they're moving away from each other, right? So this is what the Hubble's law says, right? So now the Big Bang theory says that if the galaxies are moving away from each other, sometime way in the past the galaxies must have been closer, right? So the Big Bang theory says that if the galaxies are away from each other, if you reverse time, they'll be pretty close to each other, and they estimate, now see, they're extremely close to each other, they're actually together, right? So the Big Bang theory says that 13.7 billion years ago, all the galaxies and all of the universe was just an atom, right? And after that time, that atom has expanded into the universe and into the stars and into multiple galaxies, and hence now it's moving away from each other. And another very important point is that galaxies or stars themselves are not moving, rather the fabric of the space is expanding, right? So see, these dots on my hand rather, are not moving themselves, rather my fingers, which means my hand, is opening up, which means the fabric of the space is expanding. The galaxies themselves are not moving at all, they are stationary, but the space they're in that space is expanding. So see, try to observe this again. So my hand is opening up, right? The dots themselves are not moving, rather my hand is what's opening and expanding. So the Big Bang Theory basically says that if the galaxies are expanding now, sometime way in the past, and they estimate 13.7 billion years ago, the galaxies were very close to each other, and rather they were just an atom. So now let's move on to the lecture. So this is what I just talked about. These are the three main points I talked about. So this should help you summarize everything I just said. I suggest you to take a screenshot. Now let's move on. So another concept that we should know is that now this might take some time to absorb. So I'll just tell you what it is and then I'll write it down. So there's an assumption that is made, and that assumption is that the rate of expansion is slightly lesser than slightly less than the speed of light, so that the light from the most distant star may reach us, right? So now I'll write that down, and then I'll try to explain it. So it is assumed that rate of expansion is slightly lesser than the speed of light so that light from the most distant star may reach us. So scientists love to make assumptions so that calculations are made easy. So this is very common in the field of science, you know. So that light from the most distant star may reach us. So there was a joke. Our physics teacher told us this joke. So it was like that. There was a farmer and he had some chickens, but those chickens weren't laying eggs. So the farmer's business was going down. So he went to a physicist and was like, "My chickens aren't giving eggs. Please help me. Help those chickens give eggs, right?" So the physicist went along with the farmer to his farm and studied the chicken for a long time, and then was like, "Man, there's no problem. I'll tell you one solution in just one line." And the farmer got very excited and he was like, please tell me. And the physicist was like, "Assume that the chickens lay eggs." So it's basically a very nerdy joke, because in physics there are a lot of things you need to assume, right? Just like this one, just like this assumption right here, right? So it is assumed that the rate of expansion is slightly lesser than the speed of light, so that light from the most distant star may reach us, right? So the idea here is that, for example, this is the Earth and this is the most distant star. There's no star ahead of this star, so this is the most distant star. So the idea is that the rate of expansion, which means that the recessional speed v of the star, because the star is moving away from the Earth with recessional speed v, is slightly lesser than the speed of light, because if you're observing the star, you're observing a wavelength, right? So if the speed of light is denoted by the symbol c, right? If this speed is lesser than v, then then light can never reach the earth, right? But if v is slightly lesser than c, then light can reach us. So the basic assumption is that v is the recessional speed is slightly lesser than c, and the word slightly implies that they're almost equal. So we denote almost equal with this sign. So this is an assumption we make here, and this helps with the calculation of finding of how the scientists found that the universe is 13.7 billion years old, right? So that derivation is not in the syllabus, so I won't waste time doing that. But this is something interesting that you should know, that via this assumption, scientists found out the age of the earth, right? Now there's a final thing we need to do, and that's called the redshift ratio, right? So I'll put in a heading. So the red shift ratio. Okay, so the idea here is, the idea again is the red shift basically. So for example, this is the earth, and this will be a very similar diagram to what we drew in the star. So this is the earth and this is the star, right? And the initial wavelength is, this is the wavelength that is being observed from the star to that you're observing on the earth, which is emitted by the star, right? So this is the wavelength. We'll call this the initial wavelength, right? So this is the initial wavelength. I'll write it down as well. Initial wavelength. This is situation 1, and after a few years you measured this wavelength again, and you notice that it has been redshifted, which means the wavelength has elongated because the star is further away now. So now the wavelength is longer, right? So we call this the final wavelength. Final wavelength, right? So this is the final wavelength, that's the initial wavelength, and this is after a few years, or after some time, I'm just writing after a few years as a rough estimate. So now what you do is that the difference in wavelength can be found out by subtracting the final wavelength from the initial wavelength. So the difference in wavelength can be found out by subtracting the initial wavelength from the final wavelength, right? So this is the formula for finding the difference in wavelength, right? This is the difference in wavelength. Now the redshift ratio is given by, the redshift ratio is basically I'll just tell you what it is. I'll show you what it is. Redshift ratio is equals to the redshift ratio is equals to change in wavelength upon the initial wavelength. The redshift ratio is given by the change in wavelength upon the initial wavelength, right? Now the redshift ratio can be written as V upon C. V upon C is equals to change in wavelength upon the initial wavelength, right? So V is the recessional speed, this is the recessional speed, C is the speed of light, change in wavelength is the change in wavelength, and this is the initial wavelength, right? Now the redshift ratio can also be equated to the change. This is the first thing it can be equated to, and the second thing it can be equated to is the change in frequency upon the initial frequency, because when you're increasing wavelength, the frequency decreases, right? So the formula is the same, so you need to memorize these formulas. So again, this is the recessional speed, this is the speed of light, this is the change in frequency, and this is the initial wavelength. So whenever they ask you to find the redshift ratio, you use these formulae rather, right? So I'll do a short question. Let's do a short question. Okay, something that would help is that the redshift ratio is equals to V upon C, and this V upon C is substituted right here, and in this example as well, right here. Okay, now let's do a short question. Okay, distant star is detected to have red shift value of 5.6. Okay, so since this is the ratio, it has no units because it's V upon C, so meters per second cancels out meters per second, because recessional speed and the speed of light are both speeds, right? So calculate speed at which it is moving relative to Earth. So this should tell you that they're asking for the recessional speed V, and they've given us the redshift value. So you can use this right here. Redshift ratio is equals to V upon C, and then the redshift ratio can be equated to change in wavelength upon initial wavelength, or the change in frequency upon the initial frequency, right? So now they're asking for V. They're asking for V, the recessional speed, right? So what we'll do, we need to find V. So what we'll do is that we'll equate 5.6, because 5.6 is the redshift value, the redshift ratio. So 5.6 is equals to V upon C. 5.6 is equals to V upon 3 into 10 raised to the power 8. I hope you all know that the speed of light is 3 into 10 raised to the power 8, and we get the redshift, we get the recessional speed as 5.6 into 3 into 10 raised to the power 8. And today I do have my calculator, gladly, thankfully. There it is. 5.6 into 3 into 10 raised to the power 8, and we get the value for V as 1, 2, 3, 4, 5, 6, 7, 8, 9. 1.7 into 10 raised to the power 9, rounding off to 2 sig fig. That's the answer. That's the answer for V. And that's about it for this chapter. If you have any questions, please do let me know in the comments below. We'll be doing some questions in the next video, hopefully. So I hope you understood this chapter. It's not difficult at all, but if you do have any questions, please let me know. So probably thank you for watching. Don't forget to like, share and subscribe, and please do share it with your friends, because this is a tricky chapter for some people, so it will help many people out. So thank you for watching once again. See you in the next video, guys. Thank you.